No sound. Okay. All right. Let me fix that. Let me try to fix that. Let me try to fix that. No sound. Okay. All right. And let me fix that. Let me try to fix that. Let me see what's going on here. Okay. How about now? Can people hear me now? There might have been a loose wire. I might have had a loose wire. Volume is very low. Okay, volume is very low. All right. How about now? Can people hear me a little better now? All right, thank you. I apparently had just a loose wire. There's some wire that's a little messed up on my mic. Thank you for that. All right, everyone. Welcome to World Quant Office Hours. Thank you for walking me through, making sure all systems are in check. I appreciate that. We're on week 5. And I see a question here in the chat. Ramsey says she's getting an echo. They're getting an echo. Is anyone else getting an echo, or is it just Ramsey? I want to see. Okay, Maurice says yes, that you are getting an echo. I don't know what to say. I don't know. Is there a way to reduce the echo? Ari. Okay. Anyone else observing an echo? I'm going to keep on talking so we can get more and more examples of what's going on out there, making sure there are no other echoes, no other issues. Anyone else want to chime in to see whether they hear an echo or maybe they don't hear it anymore? No echo, sorry, just had two. Oh, okay, no problem. I had 2 tabs open. All right, that makes perfect sense there. But the volume is really low. It's still very low. I can barely hear you even though all my sound... Okay, so maybe there's something wrong with my volume going through. There's probably something going on there. Let me see if I can fix that somehow. Okay. All right. Let's see. Okay. Not sure what is going on here. Echo is gone. That's good to hear. Okay. I'm not sure what's going on, of why it's so low, why the volume is so low. It's much better now. Okay. Is the volume situation better, or the echo is gone? Can you get a confirmation? All right, let's see. Can't hear you. Okay. Volume is still very low. It's okay. So still getting the volume to be very low. I see someone saying that you can't hear me at all. And let's see. All right. I don't know what's going on today. Low volume, but echo is gone. So just a low volume issue. Okay, let's see. All right. I don't know what to say. Maybe there's something wrong with my mic. Maybe my mic is breaking down or something like that. In fact, I can actually switch to my mic on my computer because I have 2 mics. I have this mic here, and I have the mic on my computer, my internal mic. So let me switch to my internal mic. I'm going to switch to my internal mic. So give me a sec while I set that up. So let's see. I'm going to go into audio capture and switch into audio input and the default. And let me turn on the mic. And let me unplug my old mic. Let me put this aside. And now I believe I'm using my internal mic, the mic that's built into my laptop. How about now? Can people hear me now? Is it better? Let me know. Because I'm using my internal mic now. An enthusiastic yes. Perfect. All right. Maybe something's going on with my mic. Maybe it's breaking down. Thank you for your confirmations. That sort of suspects. I was doing another lecture earlier today. I was having issues. My mic is breaking down apparently. I'm going to use my internal mic. It's not the best, but oh well, you can still hear me. Perhaps better than a broken, really loud now, right? So reduce the volume now, adjust your volume. So sorry if I hurt your ears. But nonetheless, let's go ahead and start things off. Appreciate the help here. Links on Jupyter Hub are incorrect order. This is placed as a Friday office hours. If I look at here, I don't, Wednesday, everything seems fine. Everything seems fine. In fact, if I open up today, then I should see myself. I should. Yeah. So keep in mind that we have one that's called the playlist, that links to the playlist, so maybe that's what you're getting confused with. But I don't see an issue. I don't see an issue with the links on Jupyter Hub. Okay. All right, we have the playlist there, so I'm not seeing this issue that you pointed out, Ramsey. But do let me know if you mean something specific. All right. And we've gone through all the mini projects. And I said, well, I have a sort of a trick up my sleeve. And one of the things that people often want to learn about, but that isn't part of the core curriculum in Unit 2, is deep learning and neural networks. So what I want to do for the rest of this week and part of next week is let's do a deep dive or a deep crash course into deep learning. Right? Let's do a crash course into deep learning. Of course, you're not going to be deep learning experts after these series of office hours. Right? That's not necessarily the goal here. My goal in this office hours and the remaining weeks and next week is for you to be exposed to deep learning. For you to have sort of a big picture, what is deep learning, what exactly it is, how does it differ from traditional machine learning, maybe play around with a little bit deep learning so you get the exposure so that later on in life you are ready to take a deeper dive into deep learning. You're ready to go all in deep learning. So that's really my goal here. So no promises. I don't expect y'all to be experts in deep learning after a few office hours. I'm going for exposure. I'm going to sort of immerse you in that field so you can be ready to address it when time later on into the future. Hopefully that's fair. All right. Let's go ahead and continue on. Okay. So do let me know if you have questions, but let's go ahead and talk about what is deep learning. Can you explain the back propagation? That's one of the things we want to talk about, right? One of the things we'll be talking about when we go into this look on neural networks and deep learning is what is this deal back propagation. A lot of this stuff will be sort of off the cuff, kind of on the fly, but oh well, a lot of drawing I will do here. Okay. So we've seen this idea of traditional machine learning models. Linear regression, logistic regression, decision tree, random forest, gradient boosting trees. All of these things are sort of the traditional machine learning models. Do we use Orange or use WQU? We'll use neither. We'll use TensorFlow. I never don't know what Orange is. I think WQU is something that's built in Java. But we'll be looking at TensorFlow when we get to the coding piece. For some of this stuff, I'm actually not going to do it on your pods because on your pods we don't have TensorFlow installed. So I'll be doing things on my personal computer, but any notebooks that I generate through our discussion here, I'll of course post it on our shared drive. Okay. So we have those traditional ML models, and they're pretty great. They're pretty powerful. In fact, let's not forget that they're rather something we want to consider. We want to use. However, there is this idea of creating these neural network models that have been shown to be pretty powerful. But with great power comes great responsibility. And a lot of the impressive applications you hear about, you see about, oftentimes underneath are powered by deep learning neural networks. In fact, I always advocate people, you don't necessarily gravitate to those methods at first. You first want to use the traditional models because a lot can be done with those traditional models. They're a lot easier to work with. With deep learning, it's more complicated. More things can go wrong. There can be more issues, longer to train. So let's not necessarily go into deep learning first. Let's first do our homework and do traditional ML models. So that's sort of my disclaimer about deep learning. But I've been using these terms, deep learning, neural networks, so I think it's a great time to define what we're working with here. So in our brain, so I'm not a biologist, so I'm going to get a lot of these details, simplify a lot of these details. But what I'm drawing here is a neuron or a brain cell. So here is a neuron or a brain cell. I see Renato is here. Welcome, Renato. Okay. So brain cell, here's a neuron. And what we have here are these, I believe these called are synapses, I believe. And I think these are called dendrites. I believe that's the term. And this is the soma. Soma for meaning the body. Dendrites for meaning trees, branches, and these are things synapses. And in our brains, we have, of course, brain cells, neurons, but they're connected to each other. They form a network or a net. In our brains, we have millions upon millions of brain cells that form connections with each other. And how they form connections with each other is you'll have this part here connected to the dendrites of a other neuron. And what happens is that some sort of electrochemical signal gets sent through the neuron. When you hear this, oh, neurons are firing, the synapses are firing, right? Maybe you hear some of those expressions. We have here very simple, two brain cells, one connected to the other, and it's sending some electrical chemical signal. That electrical chemical signal goes into the soma, this body part of the neuron, the brain cell, and it gets collected there. All the electrochemical signal goes right there into that soma, and then the brain cell will decide whether it should fire or not, where it should propagate some electrical chemical signal. So sort of like a switch, sort of the idea of a switch. It receives input, gets all summed up, and it fires or it doesn't fire. Or it might fire weakly or it might fire strongly. That's how information is transmitted in the brain. I'm not a neurologist, right? I'm not a brain scientist, so I've simplified this description, but I believe they would agree at a high level view that's kind of what's going on. Any questions about this biological idea? Okay. Do let me know. Okay. So scientists were fascinated, or sort of like, I guess, computer scientists or people who are doing modeling were fascinated by this idea of a neuron. This was back in the 50s, back in the, sorry, a little bit of history lesson, back in the 50s. It's like, well, why don't we create some sort of machine or some sort of computer that can mimic this idea of a neuron? Because fundamentally, if we can break this neuron down and say, well, a neuron is going to receive some input and then fire or not. Here, we have this, we've simplified, we abstracted away of this neuron. What if we have some sort of system or some sort of program that accepts some input? It gets summed up, and then it decides whether to fire or not. Okay, well, what we have here is this idea of an artificial neuron. An artificial neuron. Well, let's kind of describe that. Well, maybe these inputs could be something like, I don't know, x1 and x2. And their input gets weighted, gets summed up. So maybe there's some sort of weight here, W1 and W2. It gets summed up. That sum gets sent to some sort of activation function, and it fires a signal or not.
And maybe what it fires is maybe 0 or 1. So we can build a system that accepts, in this case, 2 inputs. It can be any number of inputs, but just for drawing sake, I've drawn 2 features here, x1, x2. They get weighted, they get summed up, they get run through an activation function, and it will fire either 0 or 1. And this here is our artificial neuron. What does this resemble here? What does this look like or resemble? What does this system resemble? Where have we seen something like this before? What does this remind you of? Where have we seen this idea? We have these inputs, they get weighted, they get summed, get run through an activation function, and we have an output value similar to 0 or 1. We've encountered something like this before. What was that? Someone's saying gates. So I don't think we have talked specifically about gates in this class here, but you can view this as a gate, right? You can view this as a gate. It accepts input and decides whether to open or not. Right? You can view this as logical gates. I get that. But there's something that we've seen in the class in our material that resembled this here. I totally agree with you that this we can model gates, a classifier, right? We can view, exactly. We view this as a classifier. Oh, it's 0, 1. What type of classifier does this specifically resemble, right? So you're on the right track that it resembles a classifier, but what type of classifier does this resemble? Not quite a decision tree. It resembles a logistic regression. Remember what logistic regression looks like, or what is happening with logistic regression. We have our features. They get weighted by some sort of coefficient plus an intercept. We get these logits, and we run these logits through a sigmoid function. And we have our probability. This here is basically a logistic regression classifier. We have our inputs here, just 2. They get weighted. Plus some intercept term, why not? They get weighted, they get run through an activation function. I'll call that activation function f. And we will either produce a signal of 0 or 1. This resembles exactly like a logistic regression classifier. Now the whole point here is we're trying to train, we retrain our model, we try to figure out what are the best values for our weights. W1, W2, and W naught. Right? That's the goal of what we do in machine learning. We have this forward model, we have some sort of model or framework to make predictions or return output, Now the question becomes is, can we take data to figure out the best values of our model parameters, right? That's the essence of machine learning. There's a question here. Why sometimes use sigmoid? Why sometimes use rectified linear unit, right? This goes a little bit beyond this introduction here, but we'll cross that bridge when we get there, right? We haven't discussed about different activation functions, but in short, heuristically, we've observed that using a rectified linear unit is a better activation function than a sigmoid function. Through experiments, through analysis, we figured out that empirically, the rectified linear unit works better because it's actually preventing the situation of a vanishing gradient problem. So that's sort of the nitty-gritty details here, but let's not concern ourselves about the nature of the activation function here. What we're basically setting up is a framework of a very simple neuron. A framework of a very simple neuron. Questions we have about this artificial neuron and its connection to a logistic regression classifier. Okay, do let me know. So scientists in the 50s, they built a computer. I think it was called like Mark 1 or what was it? Let me look that up. It's called the perceptron. This was called the perceptron model. Perceptron model. If I probably go to Wikipedia, I can probably show you the computer. Yes, Mark 1. Mark 1. This is an implementation of this simple perceptron model. There it is, back in the 50s. What year? It doesn't quite say, but I believe it was from the 50s. Very simple, very crude, right? That's how it was back then, right? We didn't have that much computing ability. Well, okay, this was pretty great. But we realize this is not going to be powerful enough. This is not going to be powerful enough. In fact, we can probably demonstrate this idea of perceptron and figure out cases where it fails to perform adequately. But this is not going to do so well. It's a very simple model. It cannot handle linear cases. As we've learned in class, what we have here is a linear classifier. And a linear classifier only works so well, right? It's basically drawing a line to separate two classes, or higher dimensions, drawing a hyperplane to separate two classes. I can only do so well with the hyperplane. So this idea sort of, people kind of, they poo-pooed this idea of this very simple perceptron model because of its inability to handle nonlinear cases. But it wasn't until the 80s or I believe the 70s, I forget exactly what date, where people say, you know what? Why don't we just use several perceptrons modeled together? Why don't we use several perceptrons together? Maybe this will give us a better prediction. Maybe this will better handle nonlinear cases. So we have this idea of a very simple idea of a neuron, just a single neuron. And then what we can do is, what if we have something like this? We have just two inputs right now, two inputs, x1, x2. But let's go ahead and have two neurons in a single layer. So once again, this is x1, x2. x1, x2. They go into a neuron. Right, they get weighted. I'll call this weight W1 of 2. Sorry, W1 of 1. This connection is feature 1 to neuron 2. We'll call that weight 1 of 2, W1 of 2. this neuron here, sorry, this connection here goes from feature 2 to neuron 2. So we'll call that W2 of 2. So we're using these subscripts to identify the different weights we have in our system. And now we have this other connection right here. Well, that's connecting neuron input 2 to neuron 1. So we will call that W2 of 1. What I'll go ahead and do is I'll just take a little line here and just kind of point an arrow to which line I'm referring to. It's a little bit cramped there. So before I had two weights, W1, W2, but now I have two sets of weights. One for neuron 1, one for neuron 2. And I have two neurons together. Well, what happens is that, well, these neurons, they get summed up, they fire, right? They fire. But previously, what I did is I took that output of one neuron, that was my prediction. But what I'll do instead here is, you know what? Why don't I take these two outputs and then glue them together? Sum them up together. So these return an output, they're going to fire. And what if we multiply this output with another set of weights, W1, W2, they get fed into another neuron, and then it fires the prediction, the probability. So let that system sink in here. What I have is a network of neurons. I have what's called the input layer, because that's where the input goes in. Each input gets weighted and gets sent to a different neuron. Those neurons are independent of each other. They fire. In other words, they send an output. That output gets weighted, gets summed to a third neuron, and it fires out a signal. And that is a prediction there. So here we have what is called a neural network. We have a very simple neural network with an input layer. This is called the input layer. This here is called the hidden layer. This is called the output layer. So which part is the perceptron? Well, here we no longer have a perceptron. The perceptron was just what we had before. This here, this whole thing here, this is our perceptron. And now we have multiple perceptrons glued together and fused together. So we move away from the idea of a perceptron and we use the word of a neuron. So the perceptron was a full model we had before. Here we have, we're not going to use that vocabulary anymore because we have more than one neuron. So we have neurons, this neuron, that neuron right there. So the input layer, hidden layer, output layer. Input layer because that's where the inputs go in. The hidden layer is a phrase I don't quite like, but oh well, that's used in this situation here. It's called hidden because if we were to draw a box around the system, we know the inputs, we know the outputs. And if we put this box around our model, we don't directly observe the values of what's in between. Not saying it's impossible for us to view them. It's just that if we, for some reason, draw a box around them, we know the inputs, we know the outputs, we don't readily know anything in between. So there's a multi-layer perception. You can view this as a multi-layer perception, correct. With one hidden layer. This is a very simple artificial neural network. So we have this idea of a neuron. We use more than one neuron to build a network, to have a artificial neural network. We can call ANN, as is abbreviated, artificial neural network. Well, we will probably know that we're dealing with artificial neurons, so we can simply drop it in and call it a neural network. So artificial neural network, same thing, right? If you're in the realm of machine learning data scientists, they mean the same thing. Of course, a biologist would say, well, you should make a distinction, but we're not in biology. So we can just simply call it neural network and understand that it's really an artificial neural network. Questions people have about what we've done so far, what we've built so far. All right, see the question here is, in this case, we need to specify the hidden dimensions. Right, of course, we need to specify, in this case here, how many neurons we have in this hidden layer, correct? Well, that's something we'll do when we start building these things. When we start building these networks, we would need to specify, as Maurice pointed out, is how many neurons we have in that hidden layer. Other questions people have? All right, I see. Sorry, I missed a question in the chat here. Is this like data transformations? Yeah, so Ramsey is bringing up a good point here. This kind of resembles some sort of data transformation, right? That's one of the things I was gonna ask y'all. What does this resemble, right? What does this look like, right? What does this look like, right? So this kind of looks like this idea of a pipeline, right? Wouldn't you agree that a pipeline in scikit-learn, or sort of machine learning in general, is a series of steps to get a prediction, right? We have raw data, a series of transformations, and finally a prediction. Right, this is kind of what we have here. Right, we have raw data in inputs. They get transformed, and then they get transformed to new features, and then we use those new features and we transform them again and we make a prediction. Right? As we sort of see here, it's sort of a series of transformations. Raw data to a prediction, right? Going this idea, at least for my background, I kind of view machine learning as building a workflow to produce a product, right? Produce, this whole idea that we're going to refine some raw ingredient to make something that is more valuable to us, right? And that more valuable to us is a prediction. That's exactly what's going on here. We have the framework where we have raw inputs. They go through a set of transformations, and we have a prediction. And we see what the model weights are. We see the model parameters. The model parameters are these weights fields. These weights. We have to know what they are, right? We have to learn the weights. Yeah, so going back to Ramsey's question, the last thing you have here, you can view what's happening upstream as transformations with a final prediction layer. We can view these layers as simply steps in a pipeline. And then what we have to do is we have to train our model with data so it learns the appropriate weights. When it learns the appropriate weights, those best values for the weights, it's learning the best way to transform the data. Now, we haven't talked about anything about how these are trained mechanically. Let's not worry about that right now. Let's just focus on, if we had weights, we can make a prediction. We can have a forward pass in the model. One of my goals for these series of office hours is for us to get a good feel for what's happening in deep learning and neural networks. So we defined a neuron. We define a artificial neural network, and then we can just drop that and call it a neural network. But now, we might hear the term deep learning. Right? We encountered the term deep learning, deep learning, deep learning. Well, what exactly is deep learning? Well, imagine if I were to take this network and extend it and grow it to have multiple hidden layers. And multiple, more than 2 neurons in a hidden layer. So I can take this idea of a network and grow it by length, grow it by width. Then I start having a rather deep neural network. So saying a deep neural network is a bit of a mouthful. I'm going to get tired of saying deep neural network. So I can just simply call this deep learning. So deep learning is synonymous with neural networks. Right? Deep learning is using neural networks that are deep. What is deep? Well, that is subjective, right? Sorry, that's subjective, what you consider deep. But in most applications, we go deep anyways. So strictly speaking, neural networks are not the same thing as deep learning, but often we have deep networks, so it is deep learning. And deep learning falls in this field of having, quote, deep neural networks. And what is deep? Is 1 hidden layer deep? Is 2 hidden layers deep? I wouldn't concern ourselves about a strict cutoff. Since typically when we do neural networks, we're going to have something that is more than 1 hidden layer. We'll call that deep. Let's not concern ourselves whether branding. So because of that, neural networks is synonymous with deep learning and vice versa. I see a question here in the chat, so I will address. So let me know if people have questions, right? The whole point of this here is for us to get a good understanding, a foundation of deep learning. So don't be shy and ask away. I see Ramsey's asking a question. So ML, we only fit the data once before transformation. Here we probably fitting in between. Isn't that right? So let me go ahead and read that again. So in ML, or traditional machine learning, we only fit the data once. Or we fit our model once with the training data. I agree with that. And here we're probably fitting in between. Well, in sort of traditional machine learning, you can have a series of steps, right? Let me draw the contrast of here. We can have a series of steps. So we have data, we might scale it, we might apply PCA, and then we have a regressor. So when you say we only fit the data once, we've only fit the pipeline once. But since the pipeline is multiple steps, each step is fitted on the training data. We fit the scalar, we transform. We fit the PCA, we transform. We fit the regressor. Analogous here. We have our inputs, they get weighted, they get transformed. Well, we haven't really talked about, one thing to keep in mind here is we have yet to talk about how we fit these models. So this fitting process, so we fit the model first and then we run it through. Once we have the model fitted, so we know what the parameters are, the weights specifically, we have our data, we transform it, make a prediction. All right, what's happening when we call fit on these individual steps? Who knows? Well, we know because we know in the mechanics of these models, or we're going to learn about that in more future videos. But it's very much the same. I'm not sure if that answered your question or not. Other questions people have, right? We do want to get a good feel for what's going on here. Okay, I see a question here by Maurice. So let me take a look at that there. All right, so do you compare the performance between traditional ML models and deep learning models? In this case, how do you choose a better model? Yeah, so what I recommend is before you dive into deep learning, go in the deep end of deep learning, you want to work with those traditional ML models. Why? Because they're easier to use, they're easy to train, and frankly, you can solve most problems with those traditional models. When we go into deep learning, it's more computational resource intensive, more expertise, more things to consider, as we're going to see as we dive into the mechanics of building these models. So is it really worth your time? So unless the problem you're given is one that is traditionally solved with deep learning, image recognition, for example, translational services, you get a ton of data, then that's going to push you maybe to look into deep learning first. But I always recommend people is look at those traditional models. They're easier to work with. They're easier to train. You can get an answer right away or a lot faster, right? And when we do data science, we don't do data science in a bubble, right? We're working in an organization, working for a company, and if we can get a pretty good result in 2 weeks' time, that's better than waiting a month's time for a perhaps an even better model that's slightly better, but we've wasted 2 weeks' time of work. So Maurice, what I recommend, so you might first do, let's say you do go the traditional model route, you can always use what you built initially as a benchmark. Kind of what I go through those mini projects, right? I get something that works. My thing is, let's just get something that works. Not so great in the grader, we tune it, we get a little better results. If you feel like your traditional model is not doing a good job, and you can justify that, then that might say maybe we should look into deep learning. So I always highly recommend that unless you know this is working on a problem that has traditionally always been solved by deep learning, you want to take the traditional approach at first. You can learn a lot by taking the traditional approach first. And even if you move on to deep learning, what you built has already introduced value within your organization. Can be used as a benchmark at the very least. And how do you choose the better one? Well, there's considerations in there. The simpler models might be easier to explain. If that's important for us to explain to someone how it works, then you go for the simpler models. Simpler models are faster to make predictions. If that's something important for us, we pick the simpler model. Right? Sometimes the best model isn't necessarily the one that makes the best predictions. We do want that, but there are other considerations. Any inputs, hidden layer limits? There is no limit to your hidden layer. We can have an infinitely large hidden layer, an infinite number of neurons in our hidden layer. We'll talk about that when we start building these models, but there are essentially no limits. However, we can imagine if we get it too complicated, too many hidden layers, too many neurons in a hidden layer, the model will be very complicated, very hard to train. We also might have overfitting. So consideration there. So no limit except for the limits of practicality and variance and bias. The inputs are dictated by how many features we have. So no limit there, dictated by how many features we have. See, another question here, I meant by, well, we have to get the weights for each layer. Is it equivalent to how we fit the data in ML? So we fit more than once in deep learning. You can argue we fit more than once in traditional ML. If we're using an iterative algorithm, right? We might use stochastic gradient descent to solve for model weights. In a linear regression model, well, we are calling fit more than once. This is how we call fit once, but in fit we have an iterative algorithm. Same thing with these models. Mechanically, programmatically, we call fit once, as we'll see when we build these models. Underneath the hood, it's running multiple training cycles. So that's why I sort of abstracted away this idea of fitting the model. Let's not concern ourselves with what happened right now mechanically when we call fit. The same principle applies. We call fit once on the training data. What's happening underneath the hood is we might have an iterative scheme, but we're a little bit none the wiser when we abstract it away. Let me repeat that again. Just like with traditional ML, we have our pipeline, we fit it once with the training data. We build a neural network, we fit it once with the training data. What's happening underneath the hood, what we yet to talk about, might be some sort of iterative training scheme, but that's abstracted away when we have called fit on that single model object. Other questions people have? Yet to write a single line of code. Will that be the moral? That would happen today. Maybe not write a single line of code, which is perfectly fine. You don't always have to write code. When to choose softmax activation. That's an implementation detail that's not I don't want to talk about here. But I'll just briefly say use softmax as the last activation function of the output layer. Right. We're trying to be a high overview here. So each layer has a special function. Each layer, yeah, you can view that each layer has a special function, right? You can view each layer is doing something special. Are we going for deep learning after this? Yeah, we're building up to deep learning, Sahid. We're building up to deep learning. Right? Well, you can even argue that this is deep learning here. We're gonna actually start building some of this stuff using TensorFlow, and perhaps not today, obviously, but tomorrow we can start maybe diving into building things. Nothing too fancy, but we'll see how to implement this in real life. Yeah, as Renato said, you can view that each of these layers as doing something, doing some sort of transformation. Whether we understand what that transformation is or not, that's a different story. The problem with these systems is that they're more complicated. They're a little bit of a black box. Kind of really understand what's going on half the time. That's sort of a trade-off we have, right? We want better predictions. We might lose some of that interpretability. Okay, let me think. Anything else I want to emphasize at this point here? No. Now let's talk about math. Let's describe the math of this system here. So what we have here is we have a set of weights multiplied by our features, and they get sent to these individual neurons. So what I can call here, what I'll say is at our very first input layer, I have a matrix W that gets multiplied by a vector called X. And I will draw my vector using a squiggly curly brace. We have an intercept, or a bias as it's called. This is often called the bias, unfortunately. Bias is used way too much in math and statistics. It's called the bias term. Think of it as simply an intercept. So we can describe a vector of outputs from the input layer as simply a matrix W times a vector X plus an intercept. So that is when when we fit the model is when backpropagation happens. So we haven't talked about what backpropagation is, but when we fit the model, it's going to use an algorithm called backpropagation. In neural networks applications, like in what area? Text translation, speech recognition, time series analysis, image classification. All those are all applications of neural networks. Right, so we can have this here, and we can kind of expand this further by saying, well, we put the weights in a matrix. And this will get a bit mathy. I'm not going to lie here. I'm not going to say, oh, this math is not involved. Quite a few math is involved. So this here, I can expand it out to write it out this way. Matrix multiplication. I have a 2 by 2 matrix multiplied by a 2 by 1 vector yields me a 2 by 1. So a vector of 2 rows, 1 column. Well, each value represents the different values of each of these hidden neurons right there. So this is equal to a vector of the value that gets the value that gets shot out of, no, the value that goes into each neuron in the hidden layer. We'll call that Z1 and Z2. So it's matrix multiplication. Nothing but linear algebra at the moment. Well, that was from the input layer to the output layer. No, sorry, the input layer to the hidden layer. Each neuron in the hidden layer takes its Z value and runs it through an activation function. An activation function is basically just a function, just some sort of mathematical function that will produce an output. We'll talk about what those functions are, by the way. Right? No need to focus on what those functions are. It's just going to take Z1 and give us some output we're going to call A1 or A2. That's all what that is doing right now. Here comes the inputs. They get weighted. They get summed up, fed through a function to produce an output value. So, the math at that point there, so this is our input layer. What's happening in our input layer? Input to hidden. And then here's the activation piece. Activation. We're going to call the vector of outputs A. Function accepts f, gets a vector A. So A here represents what comes out of these two neurons. And what comes out of those two neurons, well, they also get weighted and added up. Right? They also get weighted and added up. So in other words, we have, I'm going to call this Z1, and I'm going to call this Z2. Well, I'm going to just simply call it Z, because it'll only be one. What comes next is Z2, which is equal to a weight vector times A plus some bias, some intercept. I'm going to use superscripts here to keep track of things. To keep track of what layer I'm working with here. I'm going to call this B, as it's traditionally called. So I can expand this let's see. Plus B naught of 2. Okay. This is the next layer. Input activation. This comes out of the hidden layer. And then finally, we have our prediction. Which is simply running this Z through a sigmoid activation function using the symbol sigma. Why is sigmoid activation function? We're using it right now because we know it gives us values between 0 and 1, which can be treated as probabilities. If there's a better one, maybe. We'll just focus on right now just for this application here. And that is the output layer right there. So this here is the math of my system. It's purely linear algebra. Matrix and vectors being multiplied with each other, summed up, and running through functions. But do you see the symmetry? Do you see some sort of pattern or symmetry going on here that's crucial for us to understand? Notice we have w times x and now w times a. Right? Remember this idea of transformations. You can think of these neural networks as a series of transformations. So the kind of math repeats itself. So there's a nice symmetry here. What was x originally now becomes a. Of course, these are different weights. We have to solve for a different set of weights. And this is how we can write out the math of our model. Tomorrow, we want to spend some time about training, how we train these systems. But this is how it makes predictions once we have our weights. I have to go a little early today because I have something at 1, my time. But we'll take a closer look at deep learning in future office hours. Take care, everyone, and see you tomorrow.